Hi everyone, I'm Shruthi. I'm a PhD candidate at the Indian Institute of Science, Bangalore. This is a joint work with Eshaan, who is a PhD student at University of Wisconsin-Madison, and Amit, who's a researcher at Microsoft Research Bangalore, and my advisor, Anand, associate professor at IISc. I'm supported by the SIGIR 2024 student travel grant, and I'm grateful for this support and the opportunity to present here. I'm going to introduce my problem now. We look at ranking systems that influence perceptions in various domains such as news, products, and even our perceptions about individuals when they are being ranked. The problem with traditional learning to rank or the LTR models is that they optimize for utility, potentially reinforcing societal biases. Our objective was to develop LTR models that ensure fairness while maintaining high relevance. We consider randomized learning to rank algorithms because it helps us use gradient-based optimization methods. So when we look at randomized ranking algorithms, fairness could mean different things. Firstly, ex ante fairness, which asks for fairness to be satisfied in expectation, that is before the ranking has been realized. Let's look at this example where I have 12 items. 6 belong from the first group, that is the yellow 5 spiked stars, and 6 belong to the second group, the orange 6 spiked stars. Consider this distribution of giving 0.5 probability on the first ranking, which just ranks all 6 items in the top 6 ranks from the first group. And with probability half, you just show all 6 items from the second group in the top 6 ranking. So this ranking is ex ante fair because in expectation there are equal number of items from both the groups in the rankings. So here the fairness notion I'm considering is fairness of representation. In particular for this example, equal representation of either of the groups. But if you look at any sample of the ranking from this distribution, it does not satisfy the constraint that there needs to be equal representation from both the groups. Therefore, this is not ex post fair. So ex post fairness asks for fairness to be in the actual ranking after the ranking has been generated. Now consider this distribution where each ranking in the support of the distribution also satisfies equal representation. Therefore, this distribution is considered to be ex post fair. So ex post fairness is important to address some real world situations where fairness has to be very strictly enforced, or is a legal requirement where every ranking sample has to satisfy fairness rather than in expectation. Our contributions in this paper are threefold. We first propose a novel objective called ex post fair relevance that computes relevance only over fair rankings. We then give a framework for training group fair LTR models that incorporate ex post fairness and optimization. We then give an algorithm for efficiently training, particularly placket-loose ranking models for DCG utility metric. So ex post fair relevance objective, we define it as the expected relevance computed only over rankings that satisfy the group fairness constraints. For example, let us say these are all possible top 6 rankings of the 12 items. Then let's consider this distribution in whose support there are also unfair rankings according to the equal representation constraints. So the first ranking does not satisfy that constraint. Let us assume that the relevance of these rankings are these particular values. So then the ex post fair relevance turns out to be 4 because the contribution for the first ranking is 0 because it's not satisfying fairness. However, if you look at another distribution whose support always has group fair rankings, then obviously it has higher ex post fair relevance. So with this objective, we are able to identify those distributions that always satisfy ex post fair relevance, ex post fairness. So the question is, how do we optimize learning to rank models for ex post fair relevance rather than just relevance, right? So the literature in LTR has often studied optimizing for relevance under the placket-loose ranking model, which has scores assigned to each of the items. Here, for the first group, items 1 to 6, the scores, corresponding scores are S1 to S6. And for the items from the second group, the scores are S7 to S12. These are the parameters of the placket-loose distribution. So if you look at the first top 6 ranking, the probability of that seeing that ranking in the placket-loose distribution is given in the expression here. And yeah, let's just look at another example where this is a ranking, top 6 ranking with items from both the groups. So this is how the probability of sampling this ranking from the placket-loose distribution looks like. So this last expression here is for sampling the last item, the 6th item. So this is sampling from the softmax distribution of all the remaining items. Therefore, the denominator contains items from all the groups that are not in the top 5 ranks. We also consider the DCG metric. It was motivated by the previous speakers as well. So one crucial property of this metric is that the ranking utility gained by placing an item in a rank does not depend on the items placed in the rest of the ranking. So to optimize placket-loose models for expected DCG, one could consider an LTR model that takes in as input item features and predicts a score. So since we have 12 items, we'll do 12 forward passes, and then we have 12 scores that will be considered as the parameters for that particular placket-loose model. And then we could use the placket-loose sampler to sample rankings. So in order to train this LTR model, policy gradients has been a popular approach, first proposed by Singh and Joachim in 2019 to train PL models for relevance as well as fairness of exposure. And Oosterhuis in 2022 has proposed an efficient algorithm to compute gradients. This is called PL rank 3. So what happens is that after computing the scores from the LTR model via the placket-loose sampler, we sample a fixed set of rankings and use PL rank 3 algorithm to compute gradients and use these gradients to update the parameters of the LTR model. However, here it's possible that your PL sampler could sample unfair rankings. Therefore, you're not really optimizing for ex-post fair relevance. Only you're optimizing for relevance. So in order to address this, we propose to do the following. So the 12 forward passes are giving the scores, but simultaneously we use a group assignment sampler which takes fairness constraints as input, the lower bound and upper bound constraints on the number of items from each group that needs to be in the top K ranking. And it samples group assignments, that is, in the top 6 ranks, what are the groups that these ranks need to be assigned to. For example, in the first rank, it always has to be assigned to the first group. So then we give both of them as input to our group-wise placket-loose sampler, which then samples rankings while being consistent with the group assignments. That is, in the first rank, you are only allowed to sample item from group 1. So for the first step, we use our previous algorithm called sampling ex-post group fair rankings, which samples group fair rankings that satisfy several consistency as well as fairness axioms, one of which is ex-post fairness. So we use this group assignment sampler, which is the first step of this algorithm. After getting the group assignment, we then follow a group-wise placket-loose model, where here, since we can only sample an item from group 1 in the rank 1, so this would be the corresponding distribution for the top 1 ranking. And then for the second one, we sample from the group 1 items, remaining group 1 items. And for the third rank, we can only sample from the group 2. So we look at the corresponding placket-loose distribution for the top 1 ranking of items from that group, and so on. So this is how the distribution would look like for group-wise placket-loose. As you can see, it nicely decomposes into placket-loose for group 1 times placket-loose for group 2. So we then have the following result, that the ex post fair relevance, that is on the left hand side, decomposes into this nice form where it's sum over all possible group assignments that are fair, the probability of sampling that group assignment times the sum over all the groups, the group wise relevance. So one thing to note is that the group assignment sampler does not look at the scores, it only looks at the fairness constraints. So because of this, we also later show that the gradients for the ex post fair relevance with respect to the scores M of document D also decomposes nicely into this format, which is sum over all the group assignments, the probability of the group assignment times sum over all the groups, the gradient of the relevance of that sub-ranking for that particular group with respect to the scores. So we know that we can use PL rank 3 to compute these gradients efficiently. So this is our final algorithm, where after sampling rankings using our algorithm, we just apply PL rank 3 on either of the groups separately and update the LDR model. So for n items in L disjoint groups, while we sample m number of rankings to compute the policy gradients, and we are only interested in top k rankings, PL rank 3 takes time about order mn plus mk log n, and our algorithm, the group fair PL, takes time slightly longer. So n is typically of the order 10 to the 9, it could be billions. L is the number of groups, disjoint groups, it's probably very small, in the order of 10. M, we observe it to be also of the order hundreds or thousands, and K is also typically in many applications of the order of hundreds. So the additional factors in the running time here, only n matters a lot, right? So, but the dependency on n is only log, and therefore it's a reasonably longer running time. So we also have experimental results on movie lens and Kiva datasets. We use fairness of representation as to measure fairness, and DCG to measure the ranking utility. We find that this way of training LTR models, which is considered in processing, is better than the post-processing method, where you just train an LTR model to maximize relevance. After training the model, you apply post-processing algorithms to satisfy fairness. We also use the implicit bias, which was referred to by the previous speakers, where we apply a multiplicative bias on the items from the minority group. That is, the scores, observed scores of the items from the minority group are only a beta times their true scores, where beta is less than 1. So here are our results. So the left-hand side are the results when we have applied a bias of 0.7 on the minority group, and the right-hand side is when there is no bias. So the top row is the NDCG, which is measuring the ranking utility, the higher the better, and the bottom row is measuring fairness of representation. Ideally, we would want these lines to be between the upper bound and lower bounds of the representation of the groups. So PL rank 3 gold 1 is performed on the latent scores, therefore this is considered as a gold standard. However, the PL rank 3, which is optimizing for only the relevance, the red one is on the observed scores. So as you can see, when there is huge bias, then the NDCG achieved by PL rank 3 on observed scores is much lower than what it should have been. The blue and the green lines are post-processing baselines, where after maximizing for relevance, we apply a post-processing algorithm to satisfy fairness. Even this doesn't cut it. The utility for these algorithms is still much lower than what it should have been, while they satisfy fairness. However, our algorithm, the group fair PL, which is doing in processing and optimizing for ex post fair relevance, does achieve much higher relevance, almost close to the gold standard, the PL rank 3 with true scores in our experiments. There are also other experimental observations in our paper. So in conclusion, we proposed a novel approach to train ex-post fair learning to rank models. It has practical implications for fair and unbiased ranking systems. So yeah, thank you for your attention, and if you have any questions, I'm happy to take.